Up until this point, you've dealt with real numbers, numbers you use every day in life, like money and decimals and fractions and counting numbers and all that good stuff. Now we're going to start talking about complex numbers. And the complex numbers is a whole new set of numbers. It includes real numbers, but it also introduces imaginary numbers. And imaginary numbers are kind of those numbers we've just, said, no, we can't do that. No, we can't do that. Well, now we're actually going to talk about what they are and how we can use them. So before we talk about what complex and what imaginary numbers are, we need to kind of refresh what a square root is. What is a square root? And most people don't actually know what a square root is, but if I said take the square root of 4, you'd be able to tell me the square root of 4 is 2. So the square root of 4 is 2. The square root of 25 is 5. But why is that? What does square root mean? Well, a square root, if I said what is the square root of 4, I'm looking for a number that when multiplied by itself gives me 4. And that would be 2. 2 times 2 is 4. And same thing with 25. I'm looking for a number that when multiplied by itself gives me 25. Well, the only possible explanation I have for that is 5 times 5. That's what gives me 25. Therefore, the square root of 25 is 5. And you would say 5 squared is 25. And that's also, that's a relationship that squares and square roots that they have. But what if I ask you to take the square root of a negative number? And I said, what is the square root of negative 1? So that means I'm asking you, what two numbers, when multiplied, give you negative 1? They have to be the same number. So when you think about it, there's no way you can multiply the same exact number by itself and get a negative number. Because negative 1 times negative 1, that's going to give me positive 1. And 1 times 1 also gives me positive 1. So there's no way I can multiply something by itself and get a negative number. So that's what we said, well, you can't do that. You can't take the square root of a negative number by definition until we introduce this new set called imaginary numbers. So what are imaginary numbers? Well, by definition, imaginary numbers, we define imaginary numbers as I, and I is going to be the square root of 1, or square root of negative 1. So we say that the square root of negative 1 equals I. That is the definition. So we can't do it. We can't take the square root of negative 1. We don't get a real counting number we use every day. So we introduce this thing called an imaginary number. And you may also see, instead of square root of negative 1 equals I, you may see something where they square both sides, and you're left with negative 1 equals I squared. That's also a possible definition that you may see. So just keep that in mind. Now, standard form of an imaginary number, you're always going to have the real part and then the imaginary part. So an example of this would be like if we had 4 plus 2i, or 2 plus I, or something along those lines, where you have the real number where by itself is a real number, like 4 is a real number, 2 is a real number. And then you have the second part, the b. In this case, the b is 2. In this case, the b is 1. It's just implied there. And then you have the imaginary part attached to that. So now we have the imaginary part. We're good. We're going to move on. We're going to look at this set, this diagram of sets. And we talked earlier about the real numbers and what was included in the real numbers. And that is, we have irrational numbers all by themselves. And we have rational, and then inside rational we have integers, and then whole numbers, and neutral, or not neutral, natural, sorry, the counting numbers. So we have these sets. This is what we're used to. The green, everything inside the green is what we're used to. Now we're talking about introducing something new and calling the whole thing complex numbers. So when we introduce imaginary numbers with the real numbers, that becomes the set of complex numbers. So as you can see, I've put in some numbers here. 2i plus 3, I by itself, square root of negative 2, those are all imaginary numbers, and those are only in the complex set. And then inside the real numbers, you've got irrational like pi, you've got rational like 2/3, you've got integers, positive and negative whole numbers, so there's negative 1. Whole numbers include 0, and the natural numbers do not include 0. They are 1, 2, 3, 4, 5, counting on up. That's just kind of a way to show you where the imaginary numbers fall in the set of complex numbers. So we're going to do some operations in simplifying complex numbers. Just some examples. It's it's fairly simple. The one thing you have to remember is that anytime you have a negative square root, you're taking the square root of a negative number, it's going to be imaginary every single time. And you're going to break it up so you have your imaginary part and your real part. So I would break up the square root of negative 3. I would break this up into the square root of negative 1 times the square root of 3. The properties of radicals tell me I can break this up into two things that multiply to give me negative 3. Well, that is negative 1 and 3. And now I know that the square root of negative 1 is I. That's by definition. So I'm going to write I square root of 3. And that's my final answer. I square root of 3. 20 can be broken up more than 3, so I'm actually going to break this up into a perfect square. So I'm going to break this up to the negative 1. Anytime you have a negative under the radical, you always plot the negative 1. And I'm going to also break this up into square root of 4 and the square root of 5. I could do the square root of 10 and 2, but that doesn't help me. I want one of those perfect square factors. So this becomes I, this becomes 2, and this becomes square root of 5. And just for notation purposes, we put the number first, so 2i square root of 5. That's your final answer. And that's simplifying radicals. You always pull out the negative 1. Make sure you're pulling out the negative 1. Number 3 is just collecting like terms. This just shows you that just like if this were 2x plus 3 minus 4x plus 1, we do the exact same process. We're going to combine like terms, in this case the x's, and we're going to combine the numbers. Same thing here. We're going to combine the negative 4i and the positive 2i because they both are attached to an imaginary number. That's going to give me negative 2i. And then I'm going to combine the whole numbers, 3 and 1, and get plus 4. And that's it. When I'm multiplying complex numbers, you're following the same process again as if this were 2x plus 1 times 2x minus 1. You do the exact same thing. If you did 2x times 2x, you would get 4x squared. Well, here you're going to do 2i times 2i, and you're going to get 4i squared. You treat it just like a variable. So that would do first, outside, inside, last. I'm going to FOIL this. So I'm going to erase this. You see that? I did first already. Now I'm doing the outside. So that's minus 2i. Now I'm doing the inside. That's plus 2i. And now I'm doing last. Minus 1. Now this should look familiar. Anytime you have a binomial times a binomial and they're the same numbers, just different signs, that's a factor difference of two squares. So the middle will always cancel. And that leaves me with 4i squared minus 1. 4i squared minus 1. But this can simplify even further because according to definition, I squared equals negative 1. So I can actually simplify this even more by saying 4 times negative 1 minus 1, which is negative 4 minus 1, which equals negative 5. So this whole thing actually gives me negative 5. Next on number 5, I'm just going to distribute. So I'm going to distribute this I squared to here and here. And that gives me I squared, I'm sorry, not I squared, I cubed plus 2I squared. So just like before, just like with the x's, you're treating with variables, you're going to multiply I squared times I will give you I cubed, just like x squared times x will give you x cubed, and then I squared times 2 will give you 2I squared. Now you can break this up. This I squared and this I, you want to keep those separate, plus 2 times I squared. Keep that separate. The reason for that is because, again, I squared equals negative 1 by definition. So wherever there's an I squared, I can change that to negative 1. So this is actually negative 1 times I plus 2 times negative 1. So this becomes negative I minus 2. And that's my final answer. Or is it? It's not, because I need to put this in standard form. Remember, in standard form, our real number comes first and then our imaginary. So I just need to switch these around and write negative 2 minus I. That is the final answer because it's in A plus BI form. Remember that, A plus BI form. Real number and the imaginary number. So real and then imaginary. All right, and the last example we're going to do is the hardest. It's by far the hardest and what most people usually struggle with when it comes to solving these complex number problems. And that is rationalizing the denominator of a complex number. So the reason this is so hard is just because you don't recognize right off the bat what you need to do. But you're not allowed to have radicals in the denominator. You're also not allowed to have imaginary numbers in the denominator. So in order to get this out, we're going to multiply by what we call the conjugate. So if you think about this, earlier we multiplied 2i plus 1 times something, and we got rid of all the imaginary numbers. If you remember, let me scroll up a little bit, and you look, right there it is. We multiplied 2i plus 1 times 2i minus 1, and it dropped all of the imaginary numbers. The reason for that is because these two i's, they cancel. The inside terms cancel whenever you have a difference of two squares like this. This is a factor difference of two squares. These are called conjugates. Whenever you multiply by a conjugate, all of the middle terms disappear. So if I want this I to go away, I'm going to multiply by its conjugate, which is just the first number minus the second number. But I can't just multiply the denominator by 2i minus 1, because that would be changing the problem. So I have to multiply the top and the bottom by the same thing, because that is effectively 1. That right there, that actually equals 1. So I'm not changing the problem when I multiply by 1. So we're going to multiply these. And I'm actually just going to rewrite it first so you can see it. So 3 times 2i minus 1 over 2i plus 1, 2i minus 1. Now, do I really need to work this whole thing out again? Because if you just look up a little bit, you'll see that 2i plus 1 times 2i minus 1 actually equals negative 5. All the work is already done in problem number 4. So this actually just becomes 3 times 2i minus 1 over negative 5. And we're just going to distribute this 3, so it becomes 6i minus 3 over negative 5. And we don't like to leave negatives in the denominator either. We like to put them out to the side. So let's just write this as negative quantity 6i minus 3 over 5. And then last step, we're going to distribute this negative. So we get negative 6i plus 3 over 5. That is our final answer. And that's all there is to it with complex numbers. We're going to do a couple other things in class, but for the most part, if you have these basics, you'll do great.